this video lecture, I will be taking up a problem and then discussing various ways to solve the problem. We would be looking at different versions of the code implementation, and each time we would be improving upon the previous version and making it more efficient. So here's the problem. Write a Python program to test whether an anagram of a given string is a palindrome. If an anagram is a palindrome, then return boolean true, else return boolean false. What is an anagram? Given a string, then new strings created by rearranging the characters are called anagrams. Example, given a string AYD, what are the possible anagrams? YAD, YDA, DAY, DYA, ADY, AYD. So these are the possible anagrams. And what is a palindrome? A string which reads the same both in the forward and the reverse direction is a palindrome. For example, noon is a palindrome because both in the forward and the reverse directions it reads the same. Dad is again a palindrome. The string ACCA is a palindrome since reading in the forward direction or the reverse direction is the same. But the string ACCD is definitely not a palindrome because in the forward direction it reads as ACCD and the reverse direction it reads as DCCA, so they are not the same. So definitely it's not a palindrome. So we just have to see that given a string, if any of the anagram of the given string is a palindrome. So for the problem described, we would be trying to find out an algorithm for it. So let's first take some examples and then we would go to the algorithm. If an input string NNOO is given, then we know that one of the anagrams of the above string is noon, and we know that noon is a palindrome. So if you observe that this is an even length string of 4 characters, and since one of the anagrams, noon, is a palindrome, we also notice that all characters occur in pairs. So N is in pair as well as O in pairs. We don't have any unpaired characters for an even length string. Let's take another example of a string with odd length. So given a string NNOODDY, this is an odd length string with length equal to 7. So if you try to rearrange the characters, you can get the different anagrams, and you can get an anagram NODYDON, which is a palindrome. It reads the same in the forward and the reverse directions. So in an odd length string, you would notice that all the characters have pairs. Except for one character, which is kind of the middle character in the palindrome. So in this case, Y does not have a pair. So we can safely say that if an anagram of a given string has to be a palindrome, then number of unpaired characters in the string should not exceed 1. So coming to the algorithm. This algorithm is based on the logic described before. We are trying to see what is this unpaired character count. If the unpaired character count is greater than 1, we know no anagram of the given string can be a palindrome, and hence we return boolean false, else we return true. Actually, the unpaired character count is set to 0. We repeat these steps until the unpaired character count is greater than 1 or the string s becomes empty. So the idea would be to begin from the start of the string and look for a pair of characters. If a pair of characters are found, then we would remove those pair of characters from the string and then keep looking for other pairs of characters. We would be also checking for unpaired character count is greater than 1. So as soon as we have an unpaired character count greater than 1, we are going to jump out of this loop. Or in the worst case, if it's a palindrome, then the string s would become empty. This is the case for an even length string. For an odd length string with an anagram as a palindrome, then we would be left with only one character at the end. So I have marked two things in red here. One is this repeat thing and another is find C in S. So both of the statements actually depends on the input size n. So this would be the order of n, as well as this statement here, find C in S, would also be the order of n, since it depends on the length of the string. So we can say effectively that this algorithm is of the order of n square. That means the number of steps taken would be squared of the input size n. In this case, the input size is nothing but the length of the string. So do go through this algorithm described here, and we would be looking at the code implementation, the version 1 code implementation, in the next lecture. I'll be walking through Python 2 code implementation for the algorithm we discussed. This will be version 1 of our implementation. We will go through this code, profile it, and run it to get the running times and see if we could improve upon this code. The basic idea, as we discussed before in the algorithm description, would be to find the count of characters in a given string which have no pairs. If the count of such unpaired characters is greater than 1, we could infer that no anagram of the input string could be a palindrome. So let's take a look at the code. We have a while loop here, and we keep checking for this variable called as unpaired character count is less than or equal to 1. If it ever becomes greater than 1, we exit the while loop. We also exit the while loop if s becomes an empty string. We go from the start of the string to the end of the string. If we find a character which has a pair in the string, we then remove those two characters by slicing the string and continuing with our search for other characters. So in the end, we would either have an empty string, which would be the case if the given string is an even length string and one of the anagrams is a palindrome. If it's an odd length string and in case an anagram is a palindrome, then there would be only one character which has no pair. And for the case of more than one unpaired characters, we jump out of the while loop. And do take a look at the return statement here. It returns true if the number of unpaired characters is less than or equal to 1, else it returns false, which satisfies our logic. Now let's think about running this program. As you can see, I have created a few assertion statements at the bottom. Assertion is a simple way to unit test your function or your code. An assertion will fail if it evaluates to false, and that way you can catch for any bugs in your function code. For example, in this line here, if this function returns false, then false equal true is false and assertion will fail, and then you would know that your program has done something wrong. You got to fix some bug. Take a look at this last line here in this code. I've used an assertion statement. I am actually passing a huge random string which is being created from this randomize method, and in this case actually I am creating a random string of size 10,000 times 26, which is 26,000, and the whole assertion statement I have put it inside quotes, and I am passing it to a method run of the cProfile module. I have imported cProfile on the top. Let's run this program. So for an input size of 26,000, the function took 5.104 seconds. Now, this is what has actually been generated by the cProfile module. We use the run method of the cProfile module. So you can see in this line here, it generates some useful information. N calls is the number of calls, tot time is the total time, this is per call time, cumulative time, then you have file name and the line number. So if you see this total time here, you're actually seeing that the function is any anagram palindrome v1 is actually taking the maximum time, and then next highest time is taken by this index method of string objects. So you can see that actually your program is taking the maximum time. So let's find out how we can improve the program. Take a relook at the code more closely. You can see that there is a while loop here, and inside the while loop we have a for loop. So in the worst case, we could have a string of size n, and one of the anagrams of the given string is a palindrome. Then that would mean that the while loop iterates for each of the n characters until s becomes an empty string. And for the for loop starts from n characters, progressively decreasing. Maybe you could try running this program for a random input string of say 2.6 million, and you will see that it will just take too much time to complete. So maybe we should not have these two loops here. We got to get rid of one of these loops. So let's improve upon this program. You will see how we improve upon the performance in the coming lectures. We had seen in the first version of the code implementation as to how the for loop inside the while loop was a potential problem. It was increasing the time complexity. So could we do something about it? we are going to take a look at version 2 of this code. So in this version, we call the function name as is any anagram palindrome v2. You can see that it's actually just 2 lines of code here, excluding the print statement. We are going to make use of the Python built-in function reduce. Python built-in functions are extremely fast since they are written in C. The built-in function reduce takes 2 arguments. The first argument is the function remove paired character or remove paired ch, and the second argument is the string s. In Python, everything is an object. Functions are also objects. So, we can pass a function as an argument to another function. Let's try to understand how the reduce function works with the help of an example. So let's run this program for a sample input ACACD. Now, in the first pass, what is applied to the remove paired character? So rest takes the value of the character A, and ch takes the value of the second character, which is C. So that's why we got the print here as A and C. Now what does it do? It checks if C not in A, which is true, hence it returns AC. The concatenation of A plus C, A and C, that is AC. So in the next pass, the result is AC, and the third character, which is nothing but A, is passed. Now A, if we check this condition, if loop condition again, A not in AC, which is false, hence it will go to the else loop. And what it does here is it just removes the character A from result. So eventually what is passed back as the result is the character C. So hence in the next iteration you have the result C, and then the fourth character is passed, C. Eventually you will find that the only unpaired character is D, and that is the result. So the reduced string, reduced S, is nothing but the character D, and the length of the reduced string is less than or equal to 1, hence it returns true. So do look closely at this reduce function. It might look little cryptic at the beginning, but if you work out a few examples, you will be able to understand how it works. Now we are going to uncomment these assertion statements so that we can actually do a comparison between the version 1 and the version 2 of the programs. Now let's run the program again. As before, we are going to profile for an input size of 26,000. Okay, before I do that, let me comment out the print statements, otherwise we'll have a lot of clutter. Now let's run this program. So the V1 results, you see, for the 26,000 strong input, it's taking around 4.982 seconds, and if you look at the V2 results, it just takes 0.2 seconds. That's a remarkable decrease in the running time, which proves to us that the built-in function reduce actually is pretty efficient. So this is a huge decrease in the running time. So can we still improve upon this program? Let's take a look at the program again. What is happening here is the reduce function, the built-in function reduce, is going to work on all the characters of the string. And if you remember our algorithm from the previous lectures, or maybe we can just take a look at the version 1 code. Here, as soon as the unpaired character count is greater than 1, it exits the while loop. You see, we don't have to go looking for all the unpaired characters, but as soon as the unpaired character count is greater than 1, we can stop this iteration and say that none of these anagrams can be a palindrome. But here, if you see, the reduce function is going to work on all the characters. It's not going to stop as soon as we get the unpaired character count greater than 1. So you can actually see that maybe we can make it slightly more efficient. So how do we do that? Maybe we can try some other approach. So we will look at this in the next lecture. So we are going to continue improving upon the performance of the program. We have previously seen in the version 2 of the code of how we use the reduce function, and we could drastically bring down the running time. Now in this version 3 of the program, we would be taking another approach which is quite similar as before. So here what we are going to do is we are going to remove all the duplicate occurrences of the string. So by using the set function, set is again a built-in function, so it's going to be extremely fast. So new set is going to have all the characters of the string, but only the single occurrences. The duplicates would be removed. And now, instead of removing the paired characters, we are just going to count how many characters have odd occurrences. And if the number of characters with odd occurrences is greater than 1, we would know the anagram of such a string would not be a palindrome. So you can take a look at this code here. It's a simple piece of code, and I have also inserted the assert statements below. So we have all the three versions together, V1, V2 and V3. So let's run this program and see if it's going to fare better. So you can see that the version 1 took around 5 seconds, version 2 took around 0.198 seconds, that's almost 0.2 seconds, and version 3 is just taken 0.019 seconds. It's almost 6 to 7 times faster than version 2. So you can see that how we have drastically reduced the running time of the program by introducing some built-in functions as well as simplifying the logic. So let's analyze the results of the version 2 and version 3. So in version 3, you can see here the method count of the string objects is taking 0.012 seconds, and that's the highest time taken by any part of the program. And if you look at version 2, you could see that the reduce function as well as the index method was all taking time, as well as the call to the remove pad ch function. So by simplifying the program in version 3, we could drastically cut down on the time taken.